All right. Well, everybody looks super excited to be back. Little quiet. Okay. Hope everybody had a good spring break, got a little bit of time off, maybe got to do some things. A lot of people probably worked, had other things to take care of. But we are now in the second half of our current 6 weeks. In fact, 2 weeks from Friday is going to be the end of the 6 weeks, and we'll be in the final grading period of the school year. So we really don't have a whole lot more time. We got a lot of material to cover, but just not a whole lot of time. Few things about what's going to be happening this week and next week. Some good news, some bad news. I'm sure everybody's going to think of it as great news, but we have our first quiz after the break on Thursday. That's going to cover the second lesson of vectors, dot products, the projection of one vector onto another, the angle between two vectors. So by the time we take it on Thursday, it'll have been actually probably several weeks since you've actually looked at the material. So we're going to take some time tomorrow in class. I've got an exit ticket that looks very similar to the quiz you're going to take on Thursday. So I'll give you guys some time, probably 20 minutes, to go ahead and look at it together, work out the problems, kind of remember how it's done. Should be able to get those back to you on Wednesday, and that'll be another piece of material you can study in preparation for the quiz on Thursday. Okay, so that's primarily what's going to be happening this week. Next week, good news, you guys know it's going to be a short week because Monday, you guys have the day off, so you have a 3-day weekend, okay, going into this weekend. That's good for you guys. But next Thursday on the 28th is when we have our second exam. That's going to be the second exam. So I'm probably not going to worry so much about the vectors on it because of the quiz and the exit ticket we have this week. I may go ahead and put a few questions on there kind of as a review. I'll let you know if I go ahead and do that. But I'm thinking primarily it's probably going to cover sequences, arithmetic, and geometric more than anything else, the test next week. So that's what we're going to be looking at this week. Hopefully we can start series by the end of next week, and we'll continue it next week to see how far we get. Okay, so I believe that's all I have, unless anybody has any questions, anything going on we need to bring up. No? Okay, then let's go ahead and get right into it. I had to do something with first period today that I'd already had the opportunity to do with you guys, so we'll probably have some time in class today depending on how fast we're able to finish up the first set of notes. But I want to go ahead and get to the same stopping point. So we have a lot of vocabulary here. It says a blank is an ordered progression of numbers. That is a sequence. A sequence is an ordered progression of numbers. Okay, so we're going to be dealing with two different types. Either it's going to be arithmetic or it's going to be geometric. That means you're going to have a set of numbers going from one term to the next. You're either going to be adding or subtracting the same value over and over again. That's what's known as an arithmetic sequence. Or you're going to be multiplying by the same number over and over again to get the next term. That's a geometric sequence. So all of these terms here, I've got examples that I've provided. So this one here, 2, 7, 12, 17, just based on what you see, would you say that's arithmetic or geometric? Am I adding the same number over and over again, or am I multiplying by the same number over and over again to get the next term? Looks like I'm adding. In fact, what am I adding? 5. So 2 plus 5, there's the 7. Plus 5 is the 12. Plus 5 is the 17. And what would the next term be? Okay, 22. Yeah, you just keep adding the same number over and over again. Okay, so good. Now, a finite sequence has a certain number of terms. Okay, while an infinite sequence goes on forever. It has an infinite number of terms. So in our notation, the examples that I've given here, well, how am I going to know if a sequence continues forever or if it just stops? What are we going to be provided that tells me that? Like, how do I know this 1, 3, 5, 7 goes forever? The 3 dots. If you have the 3 dots at the end, that tells you whatever pattern you notice, that's going to continue beyond what we see. But like up here, the 2, 3, 4, 5, 6, those are the only elements, the terms in that sequence. Okay, so this first through the fifth. Okay, so in a recursive rule, okay, each term makes reference to a previous term. Okay, and a recursive rule. Now, there's two types of formulas that you can use when you're talking about sequences. It's going to be recursive or the other one that I'm about to mention. Now, a recursive, they're very useful, but they do have some definite drawbacks. For example, in order to use a recursive formula, you have to know the term immediately prior to the one that you're wanting. Okay, so let me see if I can go ahead and give you an example here. Now, different teachers, different resources, textbooks, they're going to use different variables from time to time, but the idea is going to remain the same. So you'll notice I have a sub 1 is equal to 3. Here, typically you're going to see probably the variable a used more than anything to represent a term, okay? But the subscript, that's going to represent whatever term number it is. So because it's sub 1, that means that 3 is the first term. Okay, so if I were to give you something like, oh, I don't know, a sub 11, that denotes what term? The 11th term. That subscript always tells you the term number that you're looking at, right? Okay, so here you'll notice we have a sub k equals a sub k minus 1 plus 5. This is an example of a recursive formula. Now again, k or n are typically the variables that we like to use for the subscript, but let's say somebody give me, let's say 7. Let's say I want the 7th term, and I'm going to use this formula that we have right here. So let's say that k is equal to 7. So the 7th term would equal a sub 7 minus 1 plus 5. Okay, well, see, all I did was plug in the 7 for k. Well, what's 7 minus 1? 6. So see, in order to find the 7th term, I have to know what the 6th term is, the term immediately before it. And that's what's bad about recursive formulas. If I wanted to know, for example, say the 100th term, I would need to know what? The 99th term. So for example, if I only know the first term, I'm given a recursive formula and I wanted the 100th, I would have to sit there using the formula and find the first, second, third, all the way to the 99th, which would then allow me to find the 100th. That's the drawback. So if it's a really large term number that you're looking for, probably recursive is not going to be the way to go. If you're looking for something small, maybe you want the 5th or the 10th term, it's not so bad. You can work that out pretty quickly. Okay. But let's say you want a faster way to go ahead and find whatever term it is. That's where the explicit rule comes in. That's a big explicit. This makes reference to a first term. Okay. Now the difference between the recursive and the explicit, well, the recursive, you have to know the term immediately prior to it. Basically, you got to know all the terms leading up to the term you want. With the explicit formula, I can immediately jump to any term I want instantaneously. Okay, I don't have to do any extra work. So this is the one that we're probably going to want to use more often. Like I said, recursive is great. There are uses for it, but for larger terms, you're probably going to want to go explicit. And in fact, you'll notice, here's an example of one. A sub n is equal to 4n minus 3. Does that look familiar? What type of form is that in? I'm thinking about a particular type of function. Slope, intercept, right? Isn't that in the mx plus b form? Okay. Because if we go back up here, okay, how are we able to tell an arithmetic from a geometric sequence? In an arithmetic, how would I always get the next term? By just adding the same value over and over again. Okay, so if I'm adding the same value over and over again, that remains constant. It can be viewed as the slope. Okay, you just need a starting point. I'm actually going to show you an example like that today. When we get to the geometric sequences, actually you're going to notice a lot of similarities between those and exponentials. Okay, because you're going to be using multiplication. All right, so let's see what else we got. So a sequence converges if the limit as n approaches infinity is a finite number, and will diverge if the limit as n approaches infinity is non-existent. Okay. Now you'll notice I've got some examples here, and we haven't seen this notation for quite some time, but of course LIM stands for what? The limit. So we read it, the limit as n approaches infinity of 1 over n. That's going to be a convergent sequence. The limit as n approaches infinity of 2 to the n, that's going to diverge. Okay, because when you think about it, if you start to look at the pattern that you have, the terms in your sequence, if they seem to approach a specific number, then you're going to say they converge. It converges on a specific value. But if it doesn't approach a specific number, like say for example 2 to the n, if it just gets infinitely large or infinitely small, if it doesn't approach something specific, then we say it diverges. Okay, and in fact, one thing that's going to really help us out when we get to this particular part of the lesson, you remember way back, one of the first things we talked about at the beginning of the year was rational functions, specifically the horizontal or oblique asymptotes. Does that sound familiar? Let me give you an easy one just to see if you guys remember this. If I were to give you something like, 3n plus 1 over n minus 2. Can anybody tell me, first off, does this have a horizontal or an oblique asymptote? And let's take a step back. What am I referring to when I say oblique? Slant. Okay. So what is this? Horizontal or slant? Okay, so horizontal. Now, how do I know? How do I tell the difference if it's a horizontal or a slant? Zach? Oh, I heard some people say it. Zach, what do you think? What would I look at in this expression that's going to help me decide horizontal or oblique asymptote? You talking about the constants? The plus 1 and the minus 2? No. That would help me with something else, though. Okay. But somebody else said it. Christian, you said it?
The degrees.
The degrees. What are you talking about with the degrees?
If it's like squared, or if it's the same on the top.
Okay, like this one here, both the degrees, the powers are the same. So does anybody remember what we do if they're the same? The coefficients. We divide the leading coefficients. So in this one here, this one would converge. Because as the value of n gets infinitely larger, we would approach 3. See, it approaches a specific number, so we say it converges. Do you guys remember the other two cases? Okay, so Aiden says if the numerator power was bigger, that's long and synthetic, that's the oblique. So what happens if the denominator's degree is larger? It's 0, it's the x-axis. See, that's all coming back to us, right? Okay, but to help us out with that, in the next day or so, I have a focus activity where we're going to be finding the horizontal and the slant asymptotes before we get into that part of this lesson. Okay, but I think that'll really help us out. Excuse me. Okay, and then these last two are basically the main topics we have for the lesson here. Each term of a geometric sequence can be determined by using a common ratio. Okay, so you remember a moment ago when I said we're going to know that we're dealing with a geometric sequence if you can multiply by the same value over and over again to get the newest term. Okay. For a geometric sequence, we call that the common ratio. The variable we use is r. We use r to describe that. Okay. So looking at this geometric sequence right here, 8, 4, 2, 1, 1/2, 1/4. Well, what am I multiplying each term by to get the next? 1/2. That's exactly right. 8 times 1/2, 4 times 1/2, 2 times 1/2, and so on. So in this case, the common ratio r would be 1/2. Okay, that's what we multiply by over and over again. Now remember, for a geometric sequence, it could be anything. It could be positive, could be negative, could be a whole number, could be a fraction. Okay. Now, each term of an arithmetic sequence can be determined by using a common difference. Okay, so here's a big difference between geometric and arithmetic. Whatever we multiply by over and over again in a geometric sequence, he's the common ratio, and we describe him using r. But the number that we add over and over and over again in an arithmetic sequence, that's what we call the common difference, and we use the variable d to represent that. Okay. D represents whatever we're adding or subtracting. Now, D can be positive or negative because really subtraction is simply adding the opposite. Okay. There we go. So in this case here, what am I going to add to 1 to get a 5? 4. And then say plus 4, plus 4, plus 4. So see, I can continue that pattern pretty easily. Okay. So we have common ratio and a common difference. Now let me go ahead and start showing you some of these formulas here. Arithmetic sequences have the same differences between the terms. So we want to look at consecutive terms. So what this is trying to tell you right here, if you take a term, you know you're dealing with an arithmetic sequence, you take a term, subtract the term prior to it that comes right before. What you get should be the common difference. And you should be able to do that for any pair of consecutive terms. So let's use this example right here. Like let's say, for example, what's 13 minus 9? 4. What's 9 minus 5? 4. What's 5 minus 1? 4. If it's arithmetic sequence, you should be able to subtract any two consecutive terms and always get the same value. That value that you get, that's your common difference. That's D. Okay. All right. So that is what this up here is talking about. And then D, of course, is the value that you get. Well, each term in an arithmetic sequence can be obtained recursively from its previous term by adding D. So this one right here, this a sub n, what they're calling the general form, this is explicit. This is one of the explicit forms you can use. Okay. Also, in this blank cell down here, I'm going to go ahead and give you another formula, but it's not going to be a recursive. It's going to be another explicit. But in order to help you out with this one right here, you'll notice dn plus c, the variables are different, but it's still what form? Yeah, it's still mx plus b. It's still that slope-intercept form, right? So in order to find c, you're going to take, what's that a sub 1? What does he represent? The first term, and you're going to subtract d. What do we call him? The common difference. Okay, so d is the common difference. That's an arithmetic sequence. R is the common ratio. That's geometric. Okay, so this little guy right here works with the dn plus c. Well, let's look at the recursion formulas. So the recursion formulas, they are based on knowing the term immediately prior to the one you want. And there's a couple of different ways you can write it. So a sub n plus 1 equals a sub n plus d. So you'll notice a sub n is the term that immediately comes before n sub 1. Okay. If you were to plug in a number, you'd be able to see that pretty easily. Like let's say n equals 3. Okay. So the third term plus d, well, what's 3 plus 1? 4. So see, a sub 4 can only be found using the third term in a recursive formula. And that works for any term number you're going to plug in. So this one right here, right next to it, is actually just another way of writing it. And truth be told, if I have to choose between the two, I'm going to go ahead and use this one right here. Okay. A sub n equals a sub n minus 1 plus d. And then we have a restriction that n's got to be greater than or equal to 2. Okay. I always like the previous term to have the minus 1. I mean, you can write it this other way. It's just a preference of mine. But is everybody okay how you can write it both ways and you still have the term before? Does anybody have any questions on that? Now, does anybody have any questions about why we need this restriction right here? Why does the term number have to be greater than or equal to 2? We can only start with 2 and then go forward. Like, what would happen if I were to plug 1 in there? There you go. Because, see, if I were to plug it in, if n equals 1, well, then I'd have a sub 1 minus 1, which would be known as the 0th term. Okay. And there are, you know, some teachers, some textbooks that do use that, but we're not. We're just going to go ahead and always start with the first term. Okay. So that's why we have that restriction there. So we can't use, say, for example, 1. Also, another thing, because we're talking about terms, you know, you're going to have a first term, a second term, a third term. So it has to be a specific term. You're not going to have a portion of a term. Like there won't be a 2.3 term. Does that make sense? It's got to be the term itself. Okay, so there won't be any decimals with respect to that. Now, for the other one down here, this is just another version of this explicit formula up here. This is the one that I like to use and I think is going to be best. A sub n is equal to a sub 1, the first term, plus n minus 1 times the common difference. Okay. That one right there is the other explicit. Okay. So actually what I like to do, if I'm looking for like a general formula that'll give me immediately any term I want, typically I'll just go ahead and plug in here, simplify it using a little bit of algebra, boom, you got your formula. Okay. But what was the difference again between a recursive and an explicit formula? Which one allows me to go to any term I want immediately? The explicit. Let's say I want to find the 75th term and I've got a recursive formula. What do I have to do? I'm going to have to find basically the first 74 because in order to get the 75th, I need the 74th term. So that is definitely one drawback to the recursive. Explicit, I don't need that. If I wanted the 75th term, I plug in, I got it. Okay. All right, well, let's take a look at an example because it's been quite a long time. I know you guys are wanting to get to some math here. I can tell. There you go. Okay. So example 1, find the first 6 terms and the 100th term for the sequence defined by the conditions b sub 1 equals -3 and b sub n plus 1 equals b sub n plus 10 for n greater than or equal to 1. Now, here's the thing. Are they providing me an explicit or a recursive? This is recursive, okay? In fact, it's based on the first version because b sub n plus 1, that's the term that would come after b sub n. Is everybody okay with that? So here's the thing. I would probably just go ahead and start substituting in, but in order to find the 100th term, I'm not going to want to use this. Okay, we're going to go ahead and I'm going to show you the explicit formula. I'm going to show you the one that I just wrote down and also the one that's already in slope-intercept form. Excuse me. Now, one other thing I want to go ahead and mention, the variable itself does not matter. Here, you know, they've done everything in terms of b. Typically, a is the most commonplace variable you're going to see. So a sub 1 equals -3. The fact that they've changed it to b's changes nothing. Okay, changes nothing. So just kind of realize that. So let's go ahead and rewrite this out. So I'm going to use the recursive formula to go ahead and get the first few terms. So it's b sub n plus 1 is equal to b sub n plus 10. Okay. So now we already have the first term, right? So let's say I want the second term. I'm going to say -3. This is when n equals 1. Okay. Because that little subscript, that's the value of n. That tells you what term number you're going for. So now I'm looking for the second term. Okay, but in order to get the second term, I've got to plug in the one prior. So I'm going to plug in n equals 1. So b sub 1 plus 1, that's your n plus 1, equals b sub 1 plus 10. Okay. See, with the recursive formula, you have to use the previous term in order to find the most current one. Well, what's 1 plus 1? So 2. So the second term would be the first term plus 10. But we already know the first term was -3. So what's the second term? 7. Okay. Okay. So now I want to find the third term. Okay. But in order to do that, I need to plug in n equals what? 2. I've got to use the previous in order to find the third. Okay. So I'm going to plug in 2 here. So b sub n plus 1 would be b sub 2 plus 1 equals b sub 2 plus 10. Well, we know 2 plus 1 is 3. And what did we find for b sub 2? We found that to be 7. So again, I'm just going to substitute in. So it looks like we're going to have 17. Okay. Remember, n is the value of the term number. So if I wanted the fourth term, I would have to plug in n equals 3. I would continue the same pattern over and over again. But at this point, I probably don't need to substitute anymore because what's the pattern? Yeah, all I'm doing is adding 10. So what would the fourth term be? 27. That's when n equals 4. If I were to plug n equals 3 into this formula, I should be getting 27. What's the next one? 37, n equals 5. And then 47, n equals 6. Okay, so I wanted the first 6 terms. There we go. Or if you don't want to go ahead and list it by n equals 1, n equals 2, well, then this would be b sub 1, b sub 2, b sub 3, and then so on. Okay. Excuse me. All right, now, let's say I wanted to go ahead and find the 100th term. Could I use this formula to do it? Yes, but do I really want to sit here and just add 10 over and over again 99 times to get to the 100th? No, we don't want to do that. I mean, we could, but it's going to take up time. We got better things to do. So I'm going to use the explicit formula. Now, the one that I gave you here, okay, is what we're going to go ahead and use. I'll come back to that other guy in just a second. But you notice how I put everything in terms of A? Remember, what did I say about the variable? It does not matter. So just to keep everything consistent, I'm going to use this formula here, but instead of A, I'm going to keep it consistent and use the B's that they have. So to find the nth term, B sub n, I'm going to take the first term plus n minus 1 times D. In fact, can anybody tell me what's the common difference here? What's the value that I'm adding over and over again? 10. So in this case, doesn't it make sense that D is equal to 10? And in fact, that's exactly what I was showing in my formula. Okay. And some people probably realized that when we first started the problem. Others, you'll see it as we start moving along and you get a little more experience. But let's go ahead and say I want the 100th term. So what's the value of n? 100. Remember, n is the term number that you're looking for. So b sub n, I'm actually looking for b sub 100. I want the 100th term. So what was the first term? Negative 3 plus, now n minus 1, I'm going to plug in the value of n that we have. We want the 100th term. So 100 minus 1 times the common difference 10. Really, when you get down to it, the sequences, series, it's just formulas and some algebra, looking at patterns. Really doesn't get any worse than that. Okay. Well, help me out here. What is 100 minus 1? 99. Whew, I got 99 problems, but math ain't one. See, that's not so much a joke, but it's a really good pop culture reference that, hopefully you guys would appreciate. Also, it's been about a week and a half, so you'd think, you'd be like, where's my jokes? I need them. Okay, anyways. So what is 99 times 10? 990 minus 3. So the 100th term should be 987. See, that's why explicit is going to be so much nicer. You can immediately jump to whatever you want. Recursive, you'd have to do a lot more work. Okay. Now, it depends, like I said, that doesn't mean that recursive isn't useful. It is very useful. There are things we're going to do with it. So we need to be aware of it because from time to time, I may even go ahead and ask you, give me the recursive formula or something like that. Okay, so you still need to be aware of those. Now, let's say we wanted to come up with a general formula in slope-intercept form for this right here that would allow me to find any term in the sequence that I want. Okay. Well, if you're wanting to find a general form, plug in all the information you know except n. Because n represents the term number, right? So that has to remain the variable you're looking for. So let's start over again. So b sub n equals, what was the first term? Negative 3 plus n minus 1 times 10. If I want to come up and create my own general formula for the sequence, I'm going to plug in all my information except n. Well, how would I simplify this?
Multiply it through by your, well, it would just be negative 3 plus n.
Okay. So Jack's right. We want to distribute first. So b sub n is equal to negative 3 plus 10n minus 10. And then what would that ultimately end up being? 10n minus 13. Now, the problem didn't ask for it, but I thought this was a really good place to start. That formula would find me any term number that I wanted. So let's test it. Let's say I did want the 100th term. So I were to plug 100 in here. So what's 100 times 10? 1,000 minus 13. There's my 987. Okay. Let's test a couple of these other ones. Like, let's test n equals 5. So let's plug 5 in there. Okay. So 10 times 5? Minus 13. 37. Okay. It'll immediately find you any value you want. Now, this is typically how I prefer to do it. That's how I was taught to do it. I always start with this general form, plug in, and then I simplify, right? But you can also do this using this information right here. Okay. I can immediately write it as dn plus c using the other formula. Okay, so let me come back over here and show you what I mean. C equals a sub 1 minus d. So let me come on down here. Okay, so C is equal to B sub 1 minus D because we're using B here. And then we also have B sub N is equal to Dn plus C. So this is the general formula that we're looking for, right? Well, what's one thing that we already have? Yeah, what's the value of D? 10. D was equal to 10. What was the very first term of the sequence? Negative 3. Okay, well, to find C, which I need for my general formula, first term was negative 3 minus the common difference 10. Well, that does give me negative 13, right? Now plug negative 13 and 10 into that. So it becomes 10n minus 13. And doesn't that look familiar? Isn't that what we got just a moment ago when we used the general formula? Okay. So either way you feel comfortable, if you want to use these two little formulas and plug in, I'm always going to use that longer explicit one because that's the one I'm more accustomed to. Okay, but either way, it does not matter. Anybody having a hard time? Any questions? Super happy to be back. Oh, I got a few yeses on that one, so there you go. Okay. Well, unless anybody has any questions, I mean, that's all I got. Okay. Like I said, we were going to have a little bit of time today. Not a lot, but, you know, better than nothing. We will continue this tomorrow. And also, remember, tomorrow we also have an exit ticket to help us remember what? Dot products, vector, source of the P, projection, there you go. The angle between two vectors, all that good stuff. Okay, let me get rid of all this. Okay, cool.